Good afternoon. Welcome to Krishna's class. So last time we considered the proof of the Lebesgue-Radon-Nikodym theorem, and I am revisiting the some of the examples that we looked at towards the end of this talk, where there was some amount of lack of clarity possibly, but I want to clear that. Okay, so that's the purpose. Right. What were those examples concerned with? they were they appeared as remarks so they were exploring what if we change the assumptions. Just look at the assumption that we have in the Lebesgue-Radon-Nikodym theorem. We are assuming mu is a positive sigma finite measure. So these are the conditions: positivity and sigma finiteness. And lambda is a complex measure. So note that every complex measure is a bounded measure. Okay. So you see that the this property is valid, that is lambda e is less than or equal to lambda x. So this acts as a bound and this is finite. So this is there the moment you assume lambda is a complex. Whereas suppose you assume lambda is a positive measure, then you cannot say that. For example, if you take lambda as the Lebesgue measure on the interval 0 infinity, then you see that this is not a bounded measure. Okay, this is really unbounded because the measure of the Lebesgue measure of the half interval is infinite, so it's not bounded. Okay, therefore a positive measure, unless you specifically say it's a bounded measure, or there are some other conditions which makes it bounded, is not going to be a bounded measure in general. So all Lebesgue measure on the interval 0 to infinity is in general an unbounded measure, whereas all complex measures are bounded measures. So this is something that you have to bear in mind. And it is this one. Suppose now we are asking the following question. What happens to the conclusions if we replace lambda by a positive measure? Okay. So we assume the following. So example, assume lambda is a positive measure. So not necessarily bounded. Unlike a complex measure. As I have pointed out, Lebesgue measure on the interval 0 to infinity is an example. But let us assume both mu and lambda are positive and sigma. Assume both lambda and mu are positive and sigma phi. So this is the assumption that we make. Then if suppose we modify it in this way, what would happen? So this is the question that you are asking. So we can write X as the union of Xn measurable subsets where lambda of finite. Because it is sigma finite, you have this. Okay. This is true for one, two, three, etc. Okay. Now the Lebesgue decomposition of this, then you see that on each xn, you see this is bounded. On each xn, this is bounded. Therefore, the Lebesgue-Radon-Nikodym theorem and we can break up lambda into lambda A and lambda S on X. Okay. So on Xn. So we can write this as lambda can be written as lambda an and lambda sn. Now you can combine them because x is union n equal to 1 to infinity xn, and you have, so we write so this is the definition of lambda a and lambda s. Then all these are uniquely determined, therefore this is a uniquely determined. Okay, right? So wherever this becomes infinite, this also would become okay, right? Therefore, so lambda xn, lambda e xn give us a Lebesgue decomposition of lambda. And we still get a function h a function h such that HTD. Okay, and once again, this is a similar combining process you can use and get the function h. Now, h is restricted to xn. They are all L1 functions on that, but h need not be an L1 function on the whole of x. Okay, so this is one conclusion that we can draw. Function, although h is locally now this means that integral over xn now this is the modification that if we use both lambda and mu as positive sigma finite measures. Now we will just give a go for another modification, namely next remark. Then what you can expect? This is the question that you are asking. So in fact, The results in the LRN theorem fail in that case. Okay, let us look at an example. We take x to be equal to the open interval 0. Mu is the Lebesgue measure. We take the sigma algebra as measurable. So M as the set of all Lebesgue measurable sets which form a sigma algebra on 0M. Now mu is the Lebesgue measure. Then we take lambda, we take as the counting measure on M. That means every Lebesgue measurable subset we are looking at and we are taking the counting measure on that. So if you take a subinterval, it's a Lebesgue measurable set and the counting measure of that is going to be infinite. Whereas if you take the singleton sets or a finite set, then it's going to be finite. So the counting measure is finite only for finite sets. Okay, that's the speciality. So clearly lambda is not a sigma finite. Mu is bounded and sigma finite. Here the finiteness of mu comes from the fact that the interval is of finite length. Okay. So now what we assert is that lambda has no Lebesgue decomposition with respect. And you see that now mu is lambda. Why? Because you take E lambda E equal to, which implies E is empty set because it is the counting measure that you are considering. Okay, so E is a subset with no elements in it. Therefore, you see this condition that lambda E equal to 0, if and only if this is true, E is the empty set, which implies mu of it is equal to 0. Therefore, This absolute continuity is satisfied. Mu is absolutely continuous. With respect to lambda. So the question that we ask next is this. Okay. Look at a specific. Okay. He asked the question, does there exist H belonging to L1 mu L1 lambda such that d mu equal to E lambda? It's the question that you are asking. Mu E equal to now we show that this is not possible. Choose a singleton set X. Okay, then mu E equal to 0, whereas lambda E equal to 1. Therefore, if then what do you get? Then what do we get? This is equal to lambda E mu e equal to 0 because it is the Lebesgue measure of the singleton set. So this is equal to 0. So we would have 0 equal to integral over e h d lambda this is equal to hx into 1, which implies now since x is an arbitrary point in 0, 1, h is identical. So we get h identically equal to 0. Okay. Suppose e is taken as interval 0, 1. Then to 1. Mu e equal to 1. Therefore, 1 equal to mu e equal to integral over e h is 1 h d lambda which is equal to 0. And this is a contradiction. A contradiction. Therefore, there does not exist any h belonging to L1 such that this result is true. Okay, that is a conclusion. Now, on the other hand, suppose you are looking for this one. What about this? Is this true? Okay. But you see that suppose you choose e equal to singleton x, then equal to 1. Therefore, what about integral over the singleton see the measure of the singleton set is 0. So this is equal to 0. Again you have a contradiction. So either way it doesn't work. Okay. So either way there does not exist an h which is L1. So this is the conclusion that therefore see modification or this to draw the conclusions of the Lebesgue-Radon recording theorem, one requires the stated conditions or the stated assumptions. Now we give the theme of today's talk, that is we work on what is called the equivalent definition of continuity. Okay. When do you say a measure is absolutely continuous with respect to another measure? This is the question. So is there any alternative definition that you can give than what we gave, or the equivalence of two statements? So theorem. Suppose mu and lambda are measures on a sigma algebra M mu positive and so we are dropping the condition that mu is sigma finite. Okay, we are not anymore assuming that. So that I will make a remark. The following conditions are what are the conditions? A, lambda is absolutely continuous with respect to mu. B, to every epsilon positive, there exists a delta positive such that absolute value of lambda e is less than epsilon for every such that mu of e is less than. Lambda is a complex measure, therefore we have the absolute value there. Here it's a positive measure, therefore we are not using that. So whenever e has the, so given epsilon, there exists a delta such that whenever e is a measurable set with the measure of e, mu of e is finite, then for that the absolute value of the or lambda e mod lambda e is less than epsilon. So this is the conclusion that we. So these two statements are equivalent. Compare this with the definition of continuity that we usually use for functions. Now here you see that you are talking about functions from defined on what? Defined on a sigma algebra. Okay. Both lambda and mu are functions defined on a sigma algebra. Okay. So we shall make some remarks, okay? Or rather, let us first prove this theorem, and then we make some remarks. So what we want to prove is this: this is our object. So we first assume, we B implies A, which is relatively simple to prove. Okay. So we prove B implies A. So assume is good. Then for any E equal to 0, mu E is less than delta. Okay, how do we prove this? So what do we want to prove? We want to prove that mu E, we want to prove that mu E equal to 0. So that's what we want to prove. Okay. So you start with mu E with all E's, any E with mu E equal to 0, then mu E is less than delta for every delta positive. That is clear. Okay. But now we assume B holds mod lambda E is less than epsilon, and that too for every epsilon positive. Okay. So what does this mean? This implies lambda E equal to therefore so that part is done. Okay. Now how to prove the second part? The second part needs little bit of constructions. Okay. What do we want to do? The second part is, so we now prove B is, B implies, sorry, A implies, B implies A, we have already proved, so A implies. But how does this one? So you see that if a statement A implies a statement B, then this is equivalent to not B that means if you take the negations, not A or not A and not B you take, that is the set where A is not valid, set where B is not valid. Okay. If what we want to prove is that if B is not valid, then A is not valid, which in turn implies if A is valid, then it implies B. Okay, so this is the strategy. So let us start with this. Suppose B is not true. We are writing down the negation of that statement. There exists a sequence of sets En belonging to M, etc., such that mu En 2 to the power minus n and mod lambda En greater than or equal to epsilon, which in turn implies the total variation of lambda on En is greater than or equal to epsilon. Okay. So this is the conclusion. This is the statement that we are making. Okay. So that is the rewriting of the statement that this. So what is happening is that for each E, there are set of E's, but what you are doing is we are choosing delta n to be equal to 2 to the power minus n. Then correspondingly you have got this conclusion. Okay, right? Therefore you get a sequence of sets E1, E2, En, etc. with this property. Now we define An to be equal to union I equal to n to infinity, starts from n, n. And we take A to be equal to intersection of so we start with E1, E2, En we have already obtained, and from that we construct sets An and A. So An is the union of En plus 1, etc. Those sets. Okay, and A is the intersection of all these. So what happens to this class of sets? See, you have the property that A1 is so it is the smallest. A1 is the smallest. This relation we have. That's clearly so from our construction. So we have so see we have mu En So we have mu of an is less than 2 to the power minus n plus 1. Look at the definition of an in terms of en. Okay, so this is what you obtain, right? And that's very easy to obtain. Okay, so you have the following. So you take mu an, and this is less than or equal to mu of sigma mu of ei starting from n to infinity, and then work it out, each one less than this. So use this inequality, and that gives you this particular inequality. Okay, and we have an n plus 1. Therefore, what do we conclude? So this implies mu a is equal to 0. Because a is the intersection of all these ans. Okay, each an has measure less than 2 to the power minus n plus 1. So what happens to a when you take the intersection from n equal to 1 to infinity of an? You get the following result. A is equal to, finally it is the intersection of all these sets, and therefore you get this result. An plus 1 is an is greater than an plus 1 also. So we use this result and find, and therefore you conclude that mu of a is equal to 0. So that means an, and that is greater than or equal to epsilon greater than 0. Okay, so mu a equal to 0. So this is the conclusion that we have. It is not B, A, and that is if and only if implies. So that concludes the proof of our theorem. Okay. So the equivalent statement. So you see, this is the reason why this particular is not obvious. When you write this symbol and we call this absolute continuity, when lambda is absolutely continuous with respect to mu, why it is true? Why this particular terminology, absolute continuity, is coming in this context? And if you look at the equivalent definition, then it is clear why the term absolute continuity is used in this context. Okay, so now we make some remarks again. the property B is absolute continuum. That is one remark. That's why we have proved the equivalence. Now, further remark is that suppose lambda is taken as a positive unbounded measure. That means instead of lambda as a complex measure where it is automatically assumed, automatically infer or automatically implied that lambda is a bounded measure. Suppose we take it as a real measure and also a positive unbounded measure. Okay, I will give an example. Yeah. Then imply the statement. Okay, so in this case we will demonstrate it, right? So let us compute that. So we take x to be equal to 0. X to be the open interval 0. Where mu is the Lebesgue measure. Okay, so essentially this will become t. Okay, because mu t equal to t. Then you can easily see that lambda of 0, 1 is equal to ln log t minus minus ln 0, which is equal to. We are taking here the measurable sets are here Lebesgue measurable sets. Zero one. Then this is the statement. For example, we'll look at this. Sets, that is the sigma algebra that you take. Lambda E equal to d mu. Suppose equal to 0. Then what you have is this. Lambda E is less than or equal to T inverse times mu. Or what you call the infimum of this. Okay. Hence, if mu e equal to 0, equal to 0. Which implies lambda is less than 1. So that is satisfied. Okay, right. But what we do is that the part B is the statement B. This is the statement B. Let us prove this. So we have obtained this mu e equal to 0, then lambda e equal to 0. But that does not mean this. For example, you take epsilon to be equal to 1 by 2 to the power e to be equal to 0 delta, and on the interval 0 to delta, this is it. That's just simple computation. Okay. That means if you take e to be the interval 0 delta or any delta, positive, mu of is equal to delta, which is positive. But lambda e lambda e which is equal to infinity. Okay. Therefore, okay. Therefore, you see that mu e equal to 0 does not imply lambda e equal to 0. Okay, right? But we have kicked out one assumption. The assumption is that, what is the assumption that we have modified? We have if you take lambda as a positive unbounded measure, the unboundedness on the finite interval comes from this factor. You see that this is 0, 1. Now you see that if you start taking intervals like this, see that they all have length, the measure infinity. Okay. The moment you drop this point and then start working out the sets, they are all going to be finite. Okay, so this 1 by t factor, okay, because the function that you have is behaves like this. Okay, so you have this problem. So if you take any interval, the closer you are to the closer you are to zero, okay, if you take any interval, then measure of that is measured using this particular integral, and that will become large. So as this left end of this interval goes to 0, you see that the interval length is going to be infinite. So this is the problem that you have. Okay, so here you are using an unbounded measure. The lambda is not bounded. Okay, right? It's real but not bounded. So that's the problem. Okay, so that gives some insight into the Lebesgue-Radon decoding theorem and the conditions that you have there. And that also gives us an equivalent condition for continuity, and probably explains why you call this absolute continuity. Thank you very much.